Hi, this is Dia Zakri. Today I will be discussing my aeroelasticity project. Our project was a flutter panel flutter speed at different altitudes. Uh, so we begin by understanding the differential equation. It's a first order differential equation. The main equation has no term, no first order time term or space term. It only has a biharmonic, which is like a second order Laplacian, and the second order time derivative. Our first step is going to be solving this equation, and then we will use the aerodynamic piston theory to add the aerodynamic pressure effects to solve the whole equation, which is in this form. We will use the assumption of W equal W times E, W in x and y times E power I omega t, and we'll search for the omega which has a negative imaginary part, because if omega has a negative imaginary part, E power I omega t will diverge, and this is our flutter speed. So first thing, we will solve it without using the aerodynamic piston theory to get the which means that we will get the natural frequencies of a clamped panel at different mode shapes. The first mode shape is symmetric about the x and y, and it's like a drum shape, and the omega 22 term is like this. But how did we get these figures? Well, we got these figures using the code that was provided to us. The code that we're given is this code, which uses panel properties and number of panels, and then uses some function that we will discuss called panel modes to get the eigenvalue and eigenvector, and then we calculate the omega, and from the omega we get the frequency, and then by changing the first frequency or second frequency and the eigenvector, we get different mode shapes for the panel. Now we know how to get the first figure. By next step is to for sea level altitude or for a fixed altitude, we want to solve the flow such that we know how the mode shape of the panel behaves. So for this, I'll show the results, and then I'll go discuss the functions. The results is symmetric about the y-axis and not symmetric about the x-axis, which is what we predict, because we only have a first order term in the x direction. The free stream is coming from 0 to 0.6, which means that the bulk or the big hump in the panel is at the trailing edge of the panel. We can also notice that the frequency of resonance frequency, or the flutter frequency, is lower than the first natural frequency with no aerodynamic loads. But how did we solve this? Okay, the code is divided into three main parts. We begin by the biggest function, the Langley plate, but this is a modified one, it's not the given one. And we start by assuming a velocity, and then we test for it. If it is a velocity that we require, the flutter velocity, then we truncate or break the loop, and if not, we continue to scan the whole velocity range. We begin by getting I'll explain this function later. It's dependent on the altitude, but we add the panel properties, which is d material, and the C2 is a coefficient of the first order spatial term. We then go to calculate the eigenvectors and the eigenvalues, and then using this we are solving the spatial part of the equation. And so to get the omega, we solve using the quadratic formula for omega plus and omega minus, and then we test the smallest omega and see the imaginary part of it. If it satisfies what we want, we have a negative difference sign, so here we test imaginary part of omega. If it's bigger than 0, then our solution diverges, and this is the flutter velocity. For this we calculate the eigenvalue and eigenvector and save them, and then calculate the frequency and save it, and Mach number and save it, and we also save the velocity at which this happened. Okay, so how do we get the eigenvalue and eigenvector? We use a function called panel modes. Panel modes, it only gets the eigenvalue and the eigenvector using a biharmonic function. It builds two matrices, which we'll discuss now, and then using this matrices multiplied by coefficients, we solve the spatial part, which is the Laplacian, second order Laplacian, the original biharmonic, and the first order special term from the aerodynamic piston theory. We then get the eigenvalues and eigenvectors and arrange them in ascending order. So what about the biharmonic? The biharmonic is a modified version of the original biharmonic that we were given. We were given that it calculates the fourth order derivative for the biharmonic term using central difference of second order, and it fills up the matrix nicely and accounts for the boundaries. And so we do the same procedure but for the first order, and we use first order central difference of second order, use central difference, which is of second order accuracy. Okay, so this is how we solve at a fixed altitude, but how about changing altitudes? Our code depends on A infinity, which is the speed of sound, and rho infinity. So we need to know how this changes with different altitudes. We made a function called altitude change, and this function has uses the standard atmosphere, and then it builds layer by layer the temperature, pressure, and density, and there are layers of constantly decreasing or increasing temperatures like this one, and of layers of constant temperature, and then we build up until we reach 105 kilometers upward. Then after we build the pressure and temperature, we calculate A infinity and therefore M infinity. We tried to add the compressibility effect, but we failed to make the code converge using the compressibility effect, and it needs further studies. We don't know exactly what happened wrong. We implemented two methods, one using direct substitution and one using iteration, and both give the code does not converge using both. So we just get the pressure and temperature and then calculate A and M infinity. Now going back to the original function to account for the changes in altitude, we make an outer loop that scans from a starting height till the end height with a certain steps per kilometer. For each one it scans for a given number of panels in the x and y direction. It scans all over the velocity and stops at the divergence velocity. So what about the results? We found that the Mach number flutter speed and flutter speed itself increases exponentially with altitude, and it really explodes. We didn't run the code until 100K because we couldn't handle the big numbers. It's extremely big and extremely slow to converge at very big altitudes. The frequency overall almost doesn't change. It only varies slightly from minimum of about 108.5 to maximum of about 112, but the velocity and Mach number significantly change. So to get a better look, we did a final run. This run was until 30 kilometers with only 30 panels and a velocity resolution of 100 meter per second. So if we now take a look at a final run, we used only 15 kilometers, and the panels were 50 by 50, and the height resolution was 5 steps per kilometer. Looking at the graph, the same trends, we can notice the same trends that flutter speed and the Mach number of flutter increases significantly with altitude. and the frequency is almost the same. It doesn't change a whole lot. So now we want to see if the values are true or not, and so we compare with the um, NASA document of Mach 3 Flutter, and we get a difference of 6% at sea level, but the error keeps increasing as altitude increase. But we have for the first big region, we have a maximum error of 6.5%, and we discuss this in details in the report. So our code is good and matches the result, but it explodes at high altitudes. We think that this is because our model is not effective at high altitudes, because the flow physics is inherently different. At high altitudes, density is significantly decreased, and so the flow properties are changed, and also at very high speeds the temperature changes the mechanical properties of the panel itself, and the boundary conditions are not clamped anymore, and they are fuzzy, and also the chemical construction of the air changes because of the very high speed and dissociation of flow, and this needs to be modeled in a more complex way. So um, our model cannot deal with extremely hard velocities or extremely high altitudes, and so we can safely say that it's very good for the first 20 or 25 kilometers, and then it can't be efficiently used. Um, the video is slightly long. I intended to make it a little bit shorter, but there are more details in the report, and I'm sorry for the surroundings, because I had to travel back to Egypt, and I'm making this video from home. Um, and thank you for the beautiful course. I watch all your lectures online, and I attended most of them in class, and thank you for all your help in explaining aero elasticity. Goodbye.